So working with similarity, we have some definitions. A transformation was it's a change to a geometric shape using various mathematical criteria. Examples include turning, formal math word is rotation, flipping, the formal math word is reflection, sliding, the formal math word is translation, and resizing, the formal math word is dilation. Here's an example of rotation and example of a reflection. Dilation is a change to a geometric shape based on multiplying the side lengths by a defined scale factor. Dilations preserve the angles in a shape but change the side lengths so a similar figure is created. Here's a dilation. Scale factor and center of a dilation. Center of a dilation, the fixed point around which all points in the figures are expanded or contracted. The center of dilation is not necessarily the center of the shape. If you're an art person, you can think of the center of dilation as the vanishing point of the figures. We can see that in that image. Scale factor is the constant number which multiplies the side lengths of the original shape to create the dilated shape. Remember, in all these, you should be writing them in the notes. Here's an example of a scale factor. Triangle ABC and triangle WTF are similar. WTF sides are half the size of triangle ABC. So the scale factor from triangle ABC to triangle WTF is 1/2. If I wanted to go the other way from triangle WTF to triangle ABC, the scale factor would be 2 because I would have to multiply all the sides in triangle WTF by 2 to get the side lengths in triangle ABC. Ratio and proportion. Ratio is a statement of how two numbers compare to each other. There are several ways to write ratios: as a fraction 2/3, with a colon 2:3, in words 2:3. Notice the one with the colon or in words are read the same way. We can also write equivalent ratios, meaning the relationship between the numbers is the same. For instance, some equivalent ratios for 2:3 could be 4:6, 10:15, 200:300, etc. Now let's say there are 10 girls and 12 boys in a typical 4th grade class. We could say the ratio of girls to boys is 10:12, 10:12, or 10/12. We can also write equivalent ratios, 5:6, 5:6, or 5/6. Proportion is a statement about the equality of two or more ratios. Let's use the example in the definition above. We can write the following proportion. 2/3 equals 4/6 equals 10/15 equals 200/300. They are all equivalent ratios. Congruent, similar, and polygon. Congruent, two shapes that are congruent are the same shape and size. This means that the angles and side lengths of the shapes are exactly the same, as we have in these two congruent polygons. Similar, two shapes that are similar are the same shape but may not be the same size. Note that the congruent shapes can also be defined as similar with a scale factor of 1. Okay. Polygon, a polygon is a straight-sided shape with at least 3 sides. Polygons can be regular, all sides are the same length, or irregular, different sides of different lengths. All of the straight-sided shapes and the examples on this page are polygons. Corresponding parts of a shape are the parts that match based on their position relative to the entire shape. So we have side AT and side ZL are corresponding sides of the two shapes. Side angle side postulate for triangle similarity. The side angle side similarity postulate says if two triangles have two corresponding sides proportional and the angles between them are congruent, then the triangles are similar. Note this only works for triangles. So here we have two similar triangles. Angle postulate. The angle similarity postulate says if two triangles have two pairs of corresponding angles which are congruent, then the triangles are similar. Note this only works for triangles because if you know two angles of a triangle, you also know the third. Right triangles are usually always similar. In this case, they definitely are because it is just a dilation from the small triangle to the big triangle. Side postulate. The side similarity postulate says if two triangles have 3 proportional pairs of corresponding sides, then the triangles are similar. Our first example is also part of practice number 4. Compare 1 and 3. So we take the short side of number 1 over the short side of number 3 and compare it to the long side of number 1 and the long side of number 3. So the short side of number 1 is 6 and the short side of number 3 is 3. So we have 6 over 3. And then we have 10 over 4. Reduce 6 over 3 is 2. 10 over 4 is 2.5. Are those equal? No. Then 1 and 3 are not similar. You need to test all of them the same way to see if any of them are similar. So you need to test 1 to 3, or compare 1 to 3, compare 1 to 2, and compare 1 to 4. Once you've compared 1 to everybody, then you can compare 2 to 3, 2 to 4. Once you've compared those, then you compare 3 to 4. Are these figures similar? What would we need to know to say that they are similar? Well, we actually don't have enough information to say the two triangles are similar. We need to know at least one more side. We need to know that BC times a scale factor of 2 results in the side length of EF. If we have that, then we know that they're similar. Or we would need to know the angle A and D are equivalent. So there's a couple different things we would need to know. But if we know one or the other, then we know if they're similar or not. What piece of information do we need to prove that triangle NQR is similar to triangle PDQ? Well, let's identify what we have first. We have that side NR, which is 7, is similar to PD, because if we take 7 times 2, we get 14. We also know that angle NQR is congruent to angle PQD, since they are both vertical angles. So we just need one more angle to show that they're congruent. So we would need to know that angle N is congruent to angle P, because those are corresponding angles, or angle R is congruent to angle D. For the figure, list all the proportions that are true. So we just need to start comparing sides. Well, we could compare side AC to BC, and that should be equivalent to AE over BD, because those are corresponding sides. We could have AC to AE, and then that would have to be BC to BD. We could have CD to CE, and that would mean BD to AE, because we're looking at similar sides. We could have CD to BD, and that would be CE to AE. Last couple examples. Create a figure that is similar to an equilateral triangle with perimeter 33 feet and explain why it's similar. Well, first off, we're told that it's an equilateral triangle, so all the side lengths are the same. So one side would be 11 feet. Now, to get a figure that's similar, I just need to take each of those sides, 11 feet, and multiply by something. Anything, multiply 11 by something, all the same number. A patio is designed using two types of tiles. The tiles are similar isosceles triangles. The lengths of the sides of the larger triangle are 6 inches and 6 inches and 4 inches. What would the dimensions of the smaller tile be? Explain why. Well, we just need to multiply them all by the same scale factor, which could also be, since we want a smaller, we could divide them all by the same number. So multiply any scale factor to each of the sides to get the similar triangle. In this case, multiply by a fraction because we want to get it smaller. Multiply by half because they're all even. So we have a rectangle. ABCD is dilated with a scale factor of 2 centered at the point 1, 1. What are the coordinates of the new figure? Well, first, plot the point 1, 1. And let's take C because it's closest. I would go up 1 and left 1 to get from my red point to C. And since it's a scale factor of 2, that means I continue that one more time. I have to go from the point, 1, 1, the distance to C twice. So I go 1, 1, and then 1, 1 again. So C is going to be at -1, 3. Do the same thing for D, and that's down 3 and left 1, and then we follow those directions again, down 3 and left 1, and we get -1, -5. Now we do A, which is down 3 and left 5, and we do those directions again, down 3 and left 5, because that's continuing the scaling twice. and that gets us to -9, -5. Do the same for A, that's going to be up 1 and left 5. We go up 1 and left 5 again, gets us to -9, 3. So there is our new figure. And what generalization can you make for the side lengths of any figure dilated with a scale factor of 2? Well, our original side lengths were 4, now they're 8. All the side lengths doubled. So take side lengths times the scale factor to get the length of the new sides. What about the area? Well, the original area is 4 by 4, which is 16. The new one's 8 by 8, which is 64. And the area quadrupled, or times by 4. So that means take the area times 2 squared, or 4, to get the new area. You always take the scale factor and take it to the power of the dimension you're looking for. So if I was looking for linear dimension, I just take it times 2 to the first power because it's one dimension. Area is 2 dimensions, so I would take the scale factor squared. If I was doing volume, I would take the scale factor cubed, so the volume would be 8 times as big as the original, because 2 times 2 times 2 is 8. Now, practice 1 is like what I just had you do. Practice 2 is looking at similar figures, are they or are they not, and we would compare ratios like the first example. Here you're trying to figure out what values would make them proportional. Here we're finishing example 1, figuring out which ones are similar to each other. Here's figuring out the ratio that we would need to compare for the two sides to be similar, two triangles to be similar. Which of these is true? So you're just picking A, B, C, or D. And 7, you're picking one of those to be true.